we have 4 terms we're working with. The mass of the barrels is pretty easy. That's just going to be the number of barrels times the number of grams per barrel. The efficiency to climb the hill, that's going to take some work because it's related to torque and the wheel diameter. Cycle time is going to take some work. We're going to have to think about what that means. Vehicle cost is not too hard though. That's just, in our competition, it's $1 per every 10 grams of your vehicle. Not including that's just the wood and the motors, not including the weights. So mostly we're going to be looking at the efficiency question and the cycle time question. I emailed everyone before the class a link to 2 files. So one of them is the average of 7 of our dyno labs. Let me download this. Dyno lab results. And I would like you to use this data for your robot design. And that's because the motors do vary tremendously. From one motor to another, you can see a 10% efficiency change. And so that we're all designing on the same level playing field, and so that we're all calculating efficiency the same way, we need to use a common set of data. So this is that common set of data based on 7 of our motors that we tested. And it hits the peak efficiency of the washers that tested at 38%, or roughly. Starts out around 10% with one washer. And here's the graphs that are related to those numbers. And I've also put in some curve fits, because these are going to be very helpful for our analysis. This is remember the RPM torque graph? So it starts out at a no-load speed of about 72 RPM. And then as you add torque, it gets slower and slower, and it does so linearly, and very, very linearly. Look at that, 0.997 for the R squared. That's as close to a fit as you get. Now, this one, a little more complex. This graph comes up to a peak and then starts to decline at a relatively linear rate if we could keep going. And I looked for a function that would fit this curve well. And so what I found was that a cubic polynomial would fit it very well. So we have an x cubed term, an x squared term, an x term, and a constant term. And you can see the black line is really following that blue line awfully closely. It's a little low there, it's a little high there, but the overall fit is also extremely good, 0.999 for the R squared. So if it was 1, that would be a perfect fit, and 0.9 would be considered good. So those are the graphs we're going to use collectively for each of the team's analysis. We talked about last time that for picking a wheel size, one strategy is, let's look at this graph, let's pick a high efficiency torque value, so something around here. That would correspond to a torque of 1.25 inch-pounds. And then you can use the equations. Our key equation, and this is for each motor, is that the torque is equal to RW sine theta, where R is the radius of the wheel. W is the weight per motor. So if you have 2 motors, you take your total vehicle weight in barrels divided by 2. If you have 4 motors, divided by 4 or whatever. And that is one way of calculating the R. That will produce the R. That will make the motors run at the efficiency, and the Greek letter for efficiency is nu, script n like that, at the n that you chose. So if you choose 1.25 inch-pounds for your torque, and you go through that T equals RW sine theta equation, then you will get indeed an efficiency running right about there. But that will not necessarily give you the highest score. Remember that that's just one of the terms right here. We also want to optimize cycle time. And this analysis does nothing for cycle time. You're going to have to analyze that separately. And so when you have efficiency divided by cycle time, who knows what the optimum diameter of the wheel is and the optimum number of barrels. So that's what we're going to do today. Okay, so let's think about our problem. Let me get a ramp and set this up. Our robot car, the starting point of the car is going to be right about here. It's going to drive to here on the flat. It's going to do a 180. It's going to drive up the ramp, deliver here, drive down the ramp, do a 180, come back to the start. So we look at that. There's basically 4 segments of what's happening. There's a segment on the flat. There's a segment up the hill, segment down the hill, segment on the flat. So if we can predict the time for each of those segments and add those times up, we've got it. We've got the cycle time. Okay, so let's see. Let's progress a little in this. Okay, 4 segments. And I'm going to draw it this way, even though it's inverted, just for clarity. So here's our first segment, 1. Here's our second segment, 2. Let me come back, 3. Back to the starting 4. Now we have to predict the speed for each of those segments. The first speed will be run at what I'll call V0. That's the speed without any particular load on it, the no load speed. The second segment, during the hill climb, that's what I'm going to have it run at V1. Now, when it turns around and comes back down, it's a very lightweight robot. It doesn't have any barrels. So it's going to, the motors will run very, very close to the same no load speed. That's just a characteristic of electric motor that if you try to overdrive it, it'll run slightly faster than that. But if you don't have a lot of weight on the robot as it comes down, it'll pretty much run at V0. So that's run at V0. And the fourth segment is also run at, of course, at V0. So the total time, oh, and all of these, let's see, let's get the distances now. So I'm going to construct it. Let's see, we know the ramp's 30 degrees. We know that the table height is approximately 30 inches. And so how do we relate those to each other? How do we know this ramp length? Yep. So sine 30 equals this distance. Maybe I shouldn't say big D. That sounds like diameter. Let's say distance over, over the distance. Therefore, the distance equals 30 over sine 30, and sine 30 is a half, so the distance is 60. Okay, that's my D. I know that speed, my general equation for speed, or velocity, is that it is a distance over a time. And therefore my time is distance over speed. So the total time is the sum of from 1 to 4 of distance over velocity. Do you know the sum sign? Is that familiar from math? Okay. All right. So 3 of these are at V0 and 1 of them is at V1. And so total time is simply going to be, the distance will come out because that's the same, we'll make that the same for each. Okay, D up, D down, and we'll make this the same just to simplify things. That's distance, same distance as that. They're all 60 inches. And that will be multiplied by 3 of our, let's see, so time equals distance over speed. So the V is on the bottom. So there's 3 of the V0s and 1 of the V1s. That'll be a prediction for time. So that's okay. Now, how do we know how to get the velocities? Okay, so that's where we have to look at how wheels work. So here is a wheel. This is a pulley, but works fine as a wheel. And I have a little index mark on it. See the little black index mark? So let's look at how a wheel rolls in terms of its revolutions and its speed. So I have this little index mark. Why don't I put it up so you can all see that more clearly? Okay, the index mark is up. And I'm going to roll it through 1 revolution starting at this point. And I'll have a little tape measure here. So I'm starting at the 0 point of the tape measure. And I'm going to roll this through 1 rev. Oop, I let it slip. Just let it roll on its own, shall we? And we'll stop it right there. Okay, so it just rolled 1 revolution, and it looks like it went about 18 3/4 inches. Okay, so this is the rollout of the wheel. So in 1 revolution, we go from the tick mark up, tick mark up. It went, what did I say? 18 3/4. 18 3/4 inches. And how do you think we could predict that based on the wheel? Circumference. So you notice that the distance around here, that's just taking, the rolling operation takes that circumference and rolls it out onto the table. And we buy that. All right. So we know circumference is formula, what is that? 2 pi r. So in 1 revolution, the wheel will travel 2 pi r. Therefore, the inches per rev is just 2 pi r. Okay, and we can verify that 18 3/4. Let's see if this all works out. This is 6. So 6 times pi, pi is about 3.14. That'd be 18, and then 15% of 6, yeah, it's about 18 3/4. Okay, so we have the inches per rev. What we're trying to get to is speed, velocity. So speed has units of inches per second or minute, but second's probably a more convenient unit. And we have inches per rev. And we also have to work with RPM. So here's RPM. RPM is the inches of revolutions per minute. So we have this unit, and we have revolutions per minute. And that's easily converted to revolutions per second, of course. 1 minute, 60 seconds. So that'll give us revolutions per second. And now notice what happens if I multiply this times that. What do I get for units? You get speed. Yeah, you get inches per second. So this equals, the inches per rev is 2 pi r. I'll do it in units first. Inches per rev times revs per second. Revs cancel, inches per second. And so if I want to find the speed, all I need to do is take 2 pi r and multiply it by 1/60. So 2 pi r over 60 times RPM. All right. Let's see. Revs per minute. So the 60 gets the RPM in the seconds, and the 2 pi r gets the rollout of that. Okay. So that is my V. And that V is going to go in one of these two, depending on the RPM that the motor is running at. In other words, on the flats, it's going at V0. So that would be what we call the no load speed, meaning no torque applied to the motor. And that would be where this line intersects this y-axis. And so that would be a little bit above 70, and it's very easily found from the equation, 72. If you wanted to be maybe a little more accurate, I mean, strictly speaking, it's going to take some torque to move the car. There's going to be some friction. And so you might use the one washer data. So that one washer data for RPM would be 70 right here. So it doesn't really matter, 70 or 72, somewhere in that range is the no load speed. Then, when you're climbing the hill, suppose you were climbing it at 1.25 inch-pounds of torque to get this high efficiency, then we would look here, 1.25, we'd come up to here, this would be the RPM that it's going at up the hill. How many followed that? Pretty good. Okay. So that would be about 55. So we do have a way of predicting the total cycle time for the entire traverse.